Okay. There were some questions from Jason regarding the problem set, and I thought I'd comment on those before beginning. So one question was what the population size is. This is problem 1 on assignment 4. That problem has you build atop and extend a previous problem from assignment 3. And in assignment 3, there's a larger population size that's explored and a smaller one, I think, right? And Jason was asking what population size should we be assuming for assignment 4 version of that, and it would be the larger population size. Okay. So the larger one. I think there was a smaller one examined for more of a special case. I don't remember the details, but in any case, it's the larger one. Okay. But then there was a second question about the units, time units specifically. And I'll give a longer answer to this, but the overall point you should keep in mind is that it doesn't really matter. You could choose to interpret time in any logic in whatever units you care to do so, as long as you're consistent. Okay. So any logic projects have a time that's maintained by the so-called AnyLogic engine, which handles events, handles the scheduling of events. Basically, its life is going from event to event to event to handle things that have to happen. And if there's a long time between events, they'll jump to that event, and therefore advance along in time. But sometimes events have to happen really quickly. Maybe, there's an earthquake happening and things have to be simulated really closely and time advances in smaller amounts. But there's a time maintained by the engine. You can actually print this out if you call get time. There's actually a time method. You may be able to also call get engine get time, but I think you could just call time. And that will give you the current simulation time, the time in the simulation. And you can set in any logic what that simulation time frame is. So if we were to go to a sample simulation here without privileging any one model, we were to go to model time, we see a start time and a stop time, right? And sometimes the stop time can be essentially infinite. So you have to manually stop it. Now, these time units here aren't specified in this particular slide. You notice it does say use a calendar, and any logic can interpret things in terms of days of the week, weeks and years, is it a weekend, and those sort of things. You can actually ask that. You can ask it to maintain a calendar, and there's actually widgets you can add from over here in the in the palette, which have to do which assume some sort of calendar interpretation of time. So somewhere within this, and I'd have to find where it is, there's a clock, for example, and that clock can display the current time as time of day, etc. So there is a calendar that can be maintained, but that's up to you if you want to subscribe to that or not. Basically, any logic is simulating things in some time units, and up associated with the model as a whole, you can actually specify what time units you want to use. And you'll notice that it provides you a set of time units, but not a complete set. If we went over here and we were to take a peek at the future and take a look at AnyLogic 7. Actually, it's not the future; it's now. And we're going to check AnyLogic 7. I believe it actually provides a larger set of time units. We can pick various things, and here we have months, years, weeks, etc. Which is kind of nice if you're dealing with a calendar notion of time. But often in models, we're dealing with a more abstract version of time. And so it is with the model in assignment 4. You're dealing with a more abstract notion of time. We don't need to have a clock on the wall that keeps track of the time within the day. We're not going to be asking if it's a weekend or something like that. So you can interpret the time in whatever form you want. And I've asked you to interpret the time, I believe, in months in this other problem in assignment 4, right? So a value of 1 would be 1 month from the beginning. 2 would be 2 months from the beginning. 3 would be 3 months from the beginning. Now suppose you have a value. Maybe it's a mean time with till recovery of 3 days. You're going to have to encode that in your model. And how do you encode it? What numeric value do you use to encode that 3 days? Well, you're going to need to do it consistently with your interpretation of time. And if you're interpreting 1 unit of time to be a month, so 0 is month 0, 1 is month 1, 2 is month 2, and the time between those, 1 time unit is 1 month, then a time frame of 3 days would be roughly 0.1 months, right? Does that make sense? So if you were to have a state chart, and you were to have transitions between states, and you wanted them to leave in exactly 3 days from the state, you would use what sort of transition? To leave in exactly that amount of time after entry? Timeout, good. And it could be a timeout of 3 days, right? But we'd encode that as a timeout of 0.1 because we're using the convention that 1 time unit is a full month, and therefore 0.1 time unit is about 3 days. That's going to be roughly 0.1, not precisely. Okay, so when we write down these values, we're going to have to be careful to write them down in numeric values that are consistent with our yardstick of time. And our yardstick of time is going to associate 1 time unit with a full month. And so if that's going to be our yardstick of time, we have to describe 3 days as about 0.1. Now, if this were a rate, what would its rate be? Suppose this weren't a timeout transition. Suppose we didn't want people to leave after exactly that amount of time, that they come in and then they all leave after exactly, 3 days or what have you. But suppose we wanted them instead to have a certain kick of the can as time goes on, they have a certain chance per unit time of leaving. That would be what sort of transition? And their time would be exponentially distributed. Their chance of leaving per unit time is constant, and therefore the chance of leaving after a certain amount of time is actually exponentially distributed. What sort of rate would that be associated with? A rate. In any logic, it's called a rate. What would that rate be for them to stay an average of 0.1 time units? An average of 3 days. It would need to be 10. It would need to be 10. Okay, the time unit associated with that, the time unit of 10 would be what?
1 day.
Time unit of this is 1 over month. Okay. It's actually 1 over month. 0.1 will be time unit of months, and the time unit associated with the rate is 1 over month. We saw that in a system dynamics model because we had a stock, we had a flow out, and we could express in a first order delay if the stock was named X, and we had a chance per unit time of leaving. Well, we'll start with the simple case. We had some mean time in the state of tau. Then the formula for this guy for the rate was what? In a first order delay, the formula was if this is some mean time, let's suppose it's mean time with infection of 0.1, what would the formula for this be? For a first order delay, it would be okay. Would it be times tau? Or it's divided by tau. Now, how do we know that? How do we know that it's x over tau? What's the quick check?
Tau is in time units.
Tau is in time units. And we know a rate is like people per month, right? People per x, per unit of time. And so whatever this is, whatever the units of x are, maybe it's people, this needs to be a formula that gives us people per time. Does that make sense? So it's got to be x divided by tau. Alternatively, though, ladies and gentlemen, so this is a mean time of 0.1 time units. Alternatively, we could phrase that as x times some alpha x, where alpha is equal to 1 over tau, or 10, right? This is 1 over a time unit, and so its units are 1 over time. And if this were a small value, you could kind of get the intuition this is sort of chance per unit time. This is actually, it is a chance per unit time. It just has to be it's a particularly high value for that. So this of time unit, the units of this, the dimensions of this are 1 over time. Okay. So my point is that when you choose a yardstick for the model, you got to be consistent about it. You got to stick with it. If your yardstick is a month, wherever you encode a value involving time, before you use it in some place where any logic cares about it, like a rate or a timeout, you need to express it as a month, in terms of months. Does that make sense to people? Now, you could, ladies and gentlemen, you could stick in a parameter in your model that's mean time infected in days. And any logic's not going to bang you on the head for doing that. Say, okay, so there's a parameter called mean time in days. But before you use it in a place that any logic cares about, it's going to calculate with it. Like in a timeout transition, or in a rate transition, or in a stock and flow context. You got to turn it into to be consistent with the yardstick you're using for the model. Now, any logic may label. It may say, oh, up here, the time unit is days, but you don't have to interpret it that way. It may print out time plot so it says days on the x-axis, and that will admittedly be a little bit awkward. But the fundamental thing is if you're consistent with your time unit, you're going to be in fine shape, and you can put something in days as long as you convert it to months before you use it. Does that make sense? So you could have a parameter that's like mean time infectious in days, and then to turn it into months, what do you do to it? Yeah, you divide it by 30, which is, not coincidentally, a number whose meaning is what? Where did you get that 30 from? So if we have something in units, 3 days, and we want to turn it into something in a certain number of months, what do we do with this thing? If we want to turn it into months, we would do what with this? We would divide it by, say, days per month. Just like dividing fractions. These two cancel. This flips up, right? Flips up. And this is like, to put it out, and this is like this times, month per day, right? And we get this day canceling with that day, and it gives some number of months. So months per day, of course, being approximately 1 over 30. So my point is that we can always convert things as long as we're consistent by the time that any logic uses it in some way. The rate transition, timeout transition, event timing, time between events, in a stock and flow equation. That's when it really matters. That's when it has to be consistent. As far as this thing is concerned, this is a nicety. This is so it labels things nicely and that sort of stuff in this version of any logic. The plot thickens in the next version where it actually keeps track of units more consistently, and if I'm not mistaken, it can do unit conversions and so on in version 7. Does that make sense? People comfortable with that? So just be consistent. If you decide that value of 1, as I asked in the problem set, is going to mean 1 month, if that's your yardstick, when you're expressing anything in the model that to any logic mechanisms, just be consistent that they're expressed relative to that yardstick, that they're expressed as like 0.1 months. That make sense? People comfortable with that? That will save you from being tripped up by it. Okay. Any other question about the problem set? Okay. We'll have one more class before it's due. So, good. So I'm going to now stop the, or should I not stop the recording? Where's PS3? Should I stop the recording or should I go on?
You can go on.
Okay. Thank you. Okay. So I'm going to stop my audio then. There we go. Okay. So last time I left you with a bit of a teaser. I left you with a bit of a riddle, a bit of a challenge. With what did that riddle have to do? It's the type of English with which I will not put. What did that riddle have? What was the focus of that riddle? Okay, well, it sounds like the riddle. This was not the riddle of the ages, the riddle of the Sphinx. It sounds like it maybe didn't occupy a great deal of your musing since our last class. I posed you a problem rooted in an actual practical problem, which is planning for West Nile. And this is an infection here in the prairies, which is not endemic. It's not a situation where year in, year out, we have a certain number of cases. It's a situation where some years we have a huge number of cases, over 1,000 in 2007, but most years we have very, very, very few recognized cases of West Nile. Why does that pose a challenge?
Very unpredictable, very seasonal.
Very unpredictable, very seasonal, and there's something even more than that. Because of that, yeah. So it would be a fool's errand, I argued, to try to formulate a single statement of what we should do. Every year you should issue an advisory on June 1st, and all throughout June you should always just do aggressive source reduction, and July 1st you should initiate larviciding or something like that. That would be not a sensible policy. If it's a really cool year, you may end up wasting a lot of money, doing a lot of work where really people aren't at risk. If it's a really bad year, it may be that you want to start the source reduction in May or what have you. So I argued that because of the variability, because of the heterogeneity temporally, we can't just stick to one plan. We can't just stay the course with a single plan. We need to be adaptive in our planning. And I noted that in this case, the mosquito populations and indeed the maturation in mosquitoes depended a lot on temperature, and temperature affected some other things like human behavior, likely to being outside and being bitten, being at risk of bitten. the degree to which people outside are actually wearing protective clothing. And so basically high temperatures lead to more mosquitoes, more virus, more people at risk by and large. Okay, less personal protective behavior. I argued that there's a dilemma here that health managers face because they want to formulate a policy to protect people, but they also want to be prudent in terms of the resources, in terms of money, and frankly, in terms of not crying wolf and having people, emerge skeptical of other advisories. They don't want to every year say, oh, watch out for West Nile, and then it's a dud, 9 out of 10 years. And then people are out there when it really gets bad, when the crunch comes and there's a real risk, the people are out there blithely ignoring the warnings, right? So the challenge here is the best policy for 1 year may be a waste or dangerous policy in another year. And, we need to make decisions taking into account uncertainties regarding the fact that weather may be changing. We may see the weather till now, but who's to know what it will do over the next few months. We don't know what the mosquito population is going to be. We don't know what the prevalence of mosquitoes in that population is going to be. We don't know what the environmental conditions. We don't know what human behavior is sometimes. And we want to be able to reason about this. And I argued that, this problem, while we've been focusing in this course implicitly on this the first type of problem, when exogenous conditions, things like temperature and rainfall, that sort of stuff, don't really have a huge impact on what choices are best, we can kind of try to identify an optimal plan. We try to find the best strategy, in general, and we can stick to that strategy year after year after year. We don't have to worry about these external conditions that much because they won't affect that much which strategy is best. We can, ahead of time, identify this thing and stick to it. But in the problem we have confronting us here, instead we have sort of a different type of problem. And these are mine, type A, type B. It's not a particularly privileged designation. I call these dynamically complex decision problems. With these problems, we're dealing with a situation, the second type of problems, when we're trying to make decisions, but the trade-off between those decisions depend hugely on what's going to go on outside of our control, things outside of our control that we can't predict ahead of time. And here we are, trying to avoid putting all our eggs in one basket. Instead of trying to stick to some fixed policy, staying the course around some fixed policy, we're trying to balance the need to learn, to observe, and to react with the need to act well ahead of time. And it's hard. We're trying to adaptively make decisions over time to take into account how long it takes our choices to have an effect at the same time as that uncertainty. So here's the quandary. How do we make decisions now when the choice of the best decision depends so much on what plays out going forward? Things beyond our control. We need to make a decision now, but we're making it in this welter of uncertainties concerning what's coming up. And should we move aggressively now, or should we kind of wait and see? Should we wait to learn and see, how's the temperature going to be trending, and then act? So, here we can't count on one particular trajectory in terms of temperature. It could go up, it could go down. Can't count on one thing. And what it does may depend a lot what's best now. And we want to consider these different possibilities of what might unfold to figure out what to do now. So the later we wait, the more information we have. But the later we wait, the more risk the cat may be out of the bag by the time we decide. The more risk that it'll be too late. And this is one of the characteristics with West Nile. Sometimes by the time they see the mosquito population being really big and having lots of West Nile on it, the cat's out of the bag. Lots of people are infected. They could try mosquito abatement strategies, but they're not going to have a big effect And basically, it's very likely you'll have a bad situation on your hand. So, how do we avoid wasting money unnecessarily? But how do we avoid putting people at risk because we're too hesitant to act? Right? So here we're trying to make a decision. What does that depend on? Well, it depends on a number of things. Certainly it depends on our current situation. I mean, after all, if it's really warm now, it's really hot right now, it's probably been a pretty good mosquito breeding season to this point. And probably more likely than not, it's going to be hot going forward. You want to consider what's going to happen in the next few weeks, maybe through weather reports, maybe through, maybe based on statistical correlations with the temperature now. And we want to consider, and this is subtle, we want to consider the fact that, look, we're making a decision now, but we're going to be meeting again. This is how these things go, week to week to week. We're going to be having the same meeting again to talk about action next week. We're going to have a chance to decide differently next week. And so, we might make one choice now, but we can recognize that next week we'll know more, and we'll have to inherit the consequences of our choices now, but we'll be able to choose something different then. So we're not deciding for all of posterity right now. So we have a flexibility built in. Our decision now is going to lock us into a strategy, and that's important. That's something we might take into account in our choices right now. We can kick the can down the road sometimes, wait and see to see what happens. Maybe we'll put it off till next week. At the same time, we might want to seize the moment and take action now so, the mosquito population doesn't have a chance to build up or what have you. So how do we deal with these things? We've been dealing with these in our group, and the basic strategy for dealing with these involves pairing up a simulation model. And this could be an H-based model, it could be a discrete event model, it could be a system dynamics model. Pairing up your simulation model with a decision tree. And I'm going to introduce decision trees. And they're the kind of final element of modeling I'm going to be teaching you. They're not commonly viewed as a dynamic model in the sense that we're talking about, but they do represent things over time. And they're worth knowing about. And they're extremely common in industry, common in many areas of academic study as well, etc. So we're going to use this thing called decision tree. The basic deal is that the simulation model is going to be, its responsibility is going to be computing consequences. So you tell it, these temperatures will happen, these decisions will be made at these times, so these temperatures occur at these times, these decisions will be made at these times, and it will spit out for you what the consequences of that. It'll say, okay, so it's a hot summer early on, and then it cools off, and we're making decisions early on to undertake source reduction, and then we go and we use some larviciding midway through the summer, and then we taper off all our strategies and wait and see how many people get infected. This is the job of the simulation model. Its job is to be told the outcome of the uncertainties. Its job is to be told the outcome of the decisions, and it figures out the consequences. It evaluates the consequences of that. The decision tree's job in life is to consider those uncertainties. It's to consider the decisions. And it's to tell the simulation model, simulate this case, and the simulation model simulates. Okay? Okay, so we're going to be introducing decision trees now. And this will be a little bit about digression, but they'll help in understanding how they fit together. So, decision trees are extremely useful instruments. I've used them many times in my own life to plan things, etc. And so we'll spend a few minutes on them. So we're going to be using decision trees both for diagrammatically illustrating decision making, and they can be used for quantitative reasoning. They're not merely tools for illustrating choices. Although they're very useful to kind of map out the set of possible choices, the policy space, so to speak. They're also used for quantitative reasoning. They're used to try to arrive at a sensible decision rule, a rule that tells you, no matter what things happen to you that you're not sure about, what's kind of the best thing for you to do in that case. It's not merely a fixed choice, typically. Instead, it's, if this happens, do this. If this other thing happens, do a different thing. And what do these decision trees consist of? Well, they represent a couple things. So decision trees, ladies and gentlemen, are used in the context where we need to make decisions over time in the context of unfolding uncertainty, and where we're interested in making our choices based on their consequences. So there'll be consequences involved depending on what choices we make that will be different if we chose A versus B. Depending on what plays out in terms of the uncertainties, there'll be different consequences. So decision trees and decision analysis are used when we have choices to make over time in the context of unfolding certainty where there are consequences to our actions. Okay? We're trying to make the best decisions. So they're representing the flow of time, choices at different points in time, uncertainties, these things called events, and consequences. Okay? There's going to be 3 types of nodes within these trees. The trees are going to consist of nodes connected by arcs, by links. And there's 3 types of basic nodes we're going to be talking about. Now, professional decision tree packages add on additional types, but these are the 3 key types. And if you go back to the classics of decision theory in the late 60s and 70s, these were the primary types used, so Schleifer and Rayfield's work, etc. And to the day, they remain sort of very, very common and fundamental building blocks. So the first type of node is shown in blue and is shown in a square. And it's called the decision node. Here you're choosing between different choices. This is up to you, what the outcome here is. You have the choice to select choice 1, choice 2, choice 3, choice 4. It's under your control. By contrast, a chance or event node is shown here in the middle. And with a chance or event node, there's some outcome that occurs, but it's not up to you. It's out of your control. And you'll notice that the chance or event node specifies more information than is associated with the decision node. Specifically, a chance and event node specifies a probability associated with each of its possible outcomes. So we don't have a choice as to which outcome comes about, but we can describe which are more likely given the situation. So we might have, probability of 0.5, possibility 1, possibility 2, 0.3, possibility 3.2. Naturally, they're mutually exclusive and collectively exhaustive. So in other words, exactly one outcome occurs in that chance node, and that outcome is exclusive of all the others. So only one occurs, and they're collectively exhaustive. It's guaranteed because it's exactly one that occurs. The probabilities have to sum to what? One. Yeah. Good. They are probabilities after all. And then finally, there's a terminal node that's shown with a triangle here. And we associate that with some consequence. It quantifies some consequence. This could be more, could be good. Maybe it's deaths averted. Maybe it's quality adjusted life years lived. Maybe it's revenues received by your company. It could be negative. This could be total deaths that are occurred. This could be number of cases of illness. This could be costs borne. But that depends on the tree. Okay, and we'll have ways of dealing with both of those. What I want to stress here is we're going to be building these trees up out of these. And you'll notice that for all of them, ladies and gentlemen, time runs along the x-axis here. So this is time here. So we're going to be going left to right. It's going to be further down in time. And naturally, the consequence nodes are on the far right. They sort of describe the consequence of a particular scenario over time. After all these decisions, particular decisions of particular events have occurred, what is the consequence born? The cumulative consequence. Does that make sense? So we have time going this way. Okay, now, having encoded this, one of the key goals of these trees is to apply a principle known as rollback, or the process known as rollback. It's associated with Bellman's principle of optimality, dynamic programming, and it's also called backwards induction, where we take the tree and we evaluate it backwards from the terminal nodes, so as to arrive at a value, an outcome for all the nodes, from the leaves, which are already given a value, up to the root of the tree, okay, up to the very head of that tree. So we're going to be going back from values associated with these nodes, which after all have to be specified when we specify the node. And we're going to be using information like the probabilities for these nodes and the nature of the decision to arrive at a value for all the nodes here. Why do we do that? Why do we arrive at a value for each of the nodes that in some sense represents the sort of the likely outcome of that situation? Why do we do that? It's so that we can make our decision, we can choose which decision to make. That's one of the big reasons. It's not the only one, but it's one of the big ones. So we could decide which decision would be best for us at this point. So we're going to be doing a rollback, and for example, the value on this node and this node, it may be that more is good in this case, and so we're going to choose which of these is greater. We're going to make that choice. Or it may be that the bigger one is bad, that its number of deaths caused, and so we choose the smaller one. Remember, decision nodes, we have the choice. We can choose which we want, and which we want will be dependent on the values of the children. On the other hand, ladies and gentlemen, event nodes, we don't have a choice. This event node, it could go either way. And we're going to associate it with a value that reflects the expected value at that point. So if you get to that point, you've made this choice here. Well, you made a choice here. This thing happened. Or you don't know which of these is going to happen. In the light of having made that choice, this is some probability, this is some probability of occurrence. And whatever the values are of these nodes, we're going to take the expected value given these probabilities. So here, each outcome has a probability, and we're going to take essentially the weighted average. It's sort of the dot product, intuitively, of these probabilities on the one hand with these values. It's the expected value. We're going to total up 0.5 there, associated with possibility 1 times the value associated with that branch. Remember, that was computed earlier because we're doing it from the root, from the bottom up. So this value, whatever it is, could be 0.5 times that, plus 0.3 times this one, plus 0.2 times that one, the value there. And we're going to give that to the value here. The idea is that you don't know which way it's going to go, and there's a certain chance we'll go one way or the other and we'll associate with the expected value. Does that make sense? Sort of the average outcome for that.
What if one of the possibilities is something that is catastrophic but has a low chance? So maybe a weighted average is not exactly the smartest way to do it all the time.
Yeah. So this is a great question, Dustin, and it shows to me once again that you're thinking about this at a deeper level, which I really appreciate. The answer lies in hidden slides. I don't have time to show you today. But the basic deal is this. We have another way of dealing it, that it's systematic. It's based on something called utility theory. And the idea is that if we have something that's catastrophic, let's take cost, okay? So suppose you're a business, okay? Suppose you're a small business. Gaining $100,000 and losing $100,000, if you're just struggling to make it, losing $100,000 is a lot worse. It affects you a lot more gravely than gaining $100,000 helps. I mean, gaining $100,000 is great, but losing it is disastrous. I mean, you're a student, right? If I ask you to flip a coin, say, hey, okay, who wants to take the challenge? Flip this coin. Who is this august man here? John Quincy Adams. I don't know why I put this coin in my pocket. John Quincy Adams in here. Okay, so you flip this coin. 50% heads, 50% tails. 50% heads, you'll win $1. 50% tails, you'll lose $1. How many people would be willing to make it to play that game? Okay. Yeah, pay $1. Okay. Suppose I were to say, same coin, 50% heads, I'll pay you $100,000. 50% tails, you pay me $100,000. Buddy. How many people have played that game?
I don't think any of us have that kind of money.
Good. That's exactly the point. That the expected value is the same, 0, right? You think, well, of course you play. And frankly, if you were Bill Gates, you'd be equally likely to play either game. Dollar, win $1, lose $1, win 100,000, lose 100,000, all in a day's work. I think Bill Gates commented one time, before 10 o'clock in the New York Stock Exchange, he loses $100 million, gains $100 million. It's kind of out in the wash. So what I'm saying is that you're onto something there. You're onto something very important, which is that when it comes to certain things, like looking at cost versus dollars is just not enough. And so we have a theory in which one of the pioneers of computer science was also involved, John von Neumann, laid out the basics of utility theory. And it basically gives a systematic way of trying to elicit people's preferences so that you know how bad is an outcome or how good is an outcome. Something to have to do with their level of satisfaction at different outcomes. And you actually then operate not in terms of dollars or in terms of deaths, but in terms of utilities on a treat like this. And that separates out the fact that you're talking about, the fact that certain things are catastrophic. Losing $100,000 for you is catastrophic. Gaining $100,000 for you is great. I don't know what to do with it, but you go and do something good. You pay off your student debts is a good thing, and do some other good things with it. But it's not as great as losing $100,000 is bad. And it captures that notion. And so we have ways of dealing with that with utility theory. And if I were giving 3 lectures in a row, maybe even 2, I would expand upon that and help you understand it. And what I might do is when I post this, I might actually lift the veil of secrecy on those hidden slides, and then you can actually see them. But very acute question, very deep question. John von Neumann would have been proud of you. Okay. Any case, good question. I don't know if I've done it justice, but the point is we have ways of dealing with that formally in decision trees. So in short, ladies and gentlemen, based on what I said, when we're performing this rollback, there's 3 simple rules. I expect you to know this. I expect to be able to do this in the final exam. If we have a terminal node, the value is given by us. We don't have to fraught it in any way. If we have an event node, we pass up the expected value of the children. Remember, we're doing it from the bottom up, so we always have computed the values for the children first, so by the time we get to an event node, we can take the expected values of these. We know the probabilities, those are given. We know the value of these guys, because they were determined earlier, so we can perform this. And so it goes recursively. So by the time we're up to this one, we've figured out these values. Does that make sense? We're doing it sort of bottom up there, right? Okay, so that's great. So for event nodes, it's expected value. For decision nodes, you select whichever child offers the best value, the best outcome. When I say best here, it could be maximum, it could be minimum. Sometimes it's maximum. If more is good, death's averted or something. Revenue. It could be You'd select the lower value if more is bad, if that's happened. Does that make sense? Okay, so here's an example tree. This is actually for West Nile. So we might have a bunch of options. Early on, week 1, we might have a choice of doing nothing. Kick the can. I don't mean that with aspersions. I mean just wait and see. We'll learn over the next week what temperatures are doing, and we'll then reevaluate. Another choice would be engage in source reduction, try to drain tires and pools, ponds that have, sloughs that have collected in a certain area, and ponds that have appeared in parks or what have you. You might do larviciding, which involves spraying, and the in a very, very heavy artillery sense, people might actually do adulticiding, which has been done once or twice here in Saskatchewan. I think once in Estevan. So those are your possible choices, and we might choose to represent those choices each week, representing the way the bug busters meetings go. People get together weekly from the province, from across health regions, the city, and they make these sort of decisions. And we're trying to inform that incremental decision-making context. So here we're going to be trying to inform what decision is made at each of these decision points. So if you end up here, or you end up here, by the vagaries of what's happened with temperature and what you've decided earlier, you'll know what to do. You'll provide them a sort of template. This seems to yield the best outcome involving whatever combination you want to look at: cost, human health, ecosystem health, long-term environmental impact, etc. And you could look at different ones and see what the outcomes are. So we're going to talk about this just to illustrate some simple things with decision trees here. So, I'm showing decision trees for the health area. These are some, more grounded in CS issues and business issues. So, imagine you're a small company and you're shipping a product, and it depends on some operating system. It depends on Windows, and Windows 8 has been delayed, suppose. To what degree are you vulnerable to that? Well, if your software, early on you decide, okay, we're going to only create our software so it does not rely on this new version of Java, or it doesn't rely on the new features of Windows 8 or what have you, then you're insulated from this. But if you do rely on it, maybe you'll have greater attraction to people who do take up your software on the new operating system. But if the new operating system is delayed, that will force essentially your product not to be able to be shipped or to be available, and so you lose money. So we might have sort of a decision here. Okay, should we rely on new features of the OS or not rely on them? And here, if we do rely on it, then we have this further uncertainty about whether the OS is going to ship in time or not. And if we wanted to choose which way to decide back here, based on these possible eventualities, we might try to associate numbers with these. And in decision analysis, there's a pretty strong latitude given in many quarters for what are known as subjectively estimated probabilities and rough and ready estimates of outcomes. And you might want to reason back using a decision rule and try to put values on these things. And using the rollback, we could get something like this. So where did this $25,000 come from? Anyone? Here's a $25,000. That's sort of the expected outcome if you're at this point. What does that mean? Or how did that get computed? Yeah. So average, weighted average. Take into account 0.1 chance here and 0.9 here, right? And so it's 0.1 times negative 200,000. Forgive me, I've written this in a sort of business accounting sort of style. So this is minus 200,000, so it's 0.1 times that, which is minus 20,000, plus 0.9 times 50,000, which is 45,000. So 45,000 minus 20,000 is 25,000, and hence this number here. And so that's kind of the the average outcome from that. And then we end up making a choice here that says, okay, well, this is better than that. This is sort of our comparison point. And in this case, we stand to gain if this happens in terms of customer uptake. We stand to lose it in terms of customer, delays till customers can get the product. And so we end up having a net value here, and that ends up this branch being better than this one, so we choose this branch. Okay? We've chosen that branch. Here's another one with a little bit more texture. Okay, so same basic option here, but suppose the new OS is delayed. Well, we could try to push the envelope. We could, even if the new OS is delayed, we could ship out, this is a dated example, we could ship out to shrink wrap stores like Future Shop or whatever that sell our software. And if we do that, maybe things will be just fine, and we'll lose less money than we would have with the OS delayed if we had just waited. On the other hand, we could be in a disastrous situation where we get it to those stores, we haven't tested it with the very latest version of the software, and suddenly we find that the ones we sold to the stores need to be updated because it's incompatible with the final version of the OS. There's some glitch or what have you. So here we have this extra level of uncertainty if we go with this nested decision to ship without waiting for the final release. If we try to push the envelope, get our software out there to the stores, if things are fine, if you feel lucky today, feature support is as expected, you end up losing less money than you would have otherwise. But if you have a bad situation where you've gotten to the stores and then you find there's a glitch, you've lost a huge amount of money. Now what's best? Well, we have this nested decisions. We can again do a rollback, and what's recommended here is okay. Wait for the OS release. Don't push. If this happens, and that's a key thing here. I want this to sink in. If you get to this point, if the new OS is delayed, then it's saying, okay, you should wait. You should wait till it finally is released. Don't try to push it. This is less favorable than that. Even though 93% of the time you can get off the hook, there is this danger of a disastrous sort of situation where we lose a lot of money. So the recommendation here, this is less advantage than that. This is more negative than that. And so what this is saying is, if we get here, then prefer this option. But, here, prefer this option. It's not guaranteed whether or not you get here. Maybe it'll go down, new OS ships in time, and you're fine. And so here, we have a decision rule specified, folks. This is a decision rule for each decision point. To wit, this one at the beginning, and this one, down here, we have a recommended outcome. It sort of recommends us, make this choice or make that choice, given our understanding of the probabilities, given our understanding of what the outcomes are. Does that make sense? Okay. So decision rules, decision trees can be used and are often used. Often the biggest motivation for them is to identify optimal decision rules. What to do under any of these circumstances. If it's a hot summer early on, if it's cold summer early on, if it continues to be hot later or not. Each of those points will form some understanding of what we've got. So asking in health region, could kind of look up, okay, what are mosquito numbers now, temperatures now, etc. And maybe have some sense as to kind of, given their sense of what's important, what would be the best outcome to try right now. And sometimes it'll be wait and see for the next week. Right? So a decision rule will specify what we will recommend some choice for every decision rule, given any possible eventuality to this point. Take into account that flexibility we have. And often that choice will be wait. Not always, but often we wait. Okay, so, we may have a decision tree that can be quite bushy, quite big. And we may have a given scenario involving a set of choices and events over time. So remember, time is running left to right here. And here we have a scenario associated with make this choice, this outcome happens out of our control. We make this choice, this outcome happens, and we get some consequence at the end. Does that make sense? This this scenario has some consequence, right? Okay, so a bit of terminology here. A static decision rule, these are things you're responsible for. A static decision rule is a decision rule. It specifies what to do for every possible decision point you can reach. But it's always making the same predetermined decisions, regardless of eventualities. At the same point in time, you'll always make the same outcome. An adaptive decision rule, by contrast, is going to vary its decisions based on what events have occurred. So let's take a look at each of these. This is a static decision rule. Why do I say it's a static decision rule? How would you, if I put this on the final exam, and I asked, is this decision rule static or is it adaptive? How would you know it's static? What's sort of the hallmark to look for?
You do nothing in every case.
Good.
Except for the last.
Yeah, good. Yeah. Curtis hit it right on the nail. So here we have these decisions here.
Except for the last one, larva side.
Well, but you're still doing the same thing. You're doing the same thing in each case, and that's the defining thing. So here we're undertaking the same action here, no matter what event occurred before us, whether we went this way or that way. We're making the same action here. We're choosing the same thing. Do nothing here. Now, this way, we're also making the same action, though, and that's the rub. So here, if we're ending up here, no matter which way this event went, we're making the same choice here. And if we showed this up here, it would need to be the same up here. So look, no matter which ways the events are going, we're making the same decisions. At week 3, we're doing larviciding. Or week 2, we're doing larviciding. At week 1, we're doing nothing. Do you see why that's static? It's staying the course. It's just saying, do this. Do this thing. It would be like we tell the Buzzbusters meetings, okay, week 1, issue an advisory. Week 2, do nothing. Week 3, do larviciding. It's static. They don't even need to look at mosquito numbers. They don't need to look at temperature. They don't need to look at rainfall. They don't need to look at West Nile penetration. They just do the same thing. It's static. It's fixed. It's involved in a fixed strategy. Does that make sense? And for a lot of problems that are not of this type, for a lot of the problems we discuss in the course, this may be enough, But for another broad class of those problems like beat problems, we need something more than that. We need an adaptive rule. Here, we have an adaptive rule. Who can spot the signs of adaptiveness? Why is this rule unlike the other one? What's different? Could anyone point out to me a place that's different? Is that a hand or is it a... So, what's different from this from the previous one?
At t equals week 1.
Good.
I guess you're taking a different decision in one of the routes.
Good. You're taking a different decision. So if it was hot, if it was hotter, then we're larviciding. Otherwise, we're doing nothing. So we're making a different choice based on the temperature. Do you see that? We're making, in this case, lower temperature, we're doing nothing. Otherwise, we're larviciding. We're making a different... The previous one had both these doing nothing. Here, we're making a different choice here. Does that make sense? You see that? This is key. So if I gave you this on the final exam, you could help me? Okay, good.
I don't really understand.
Okay, so a static decision rule, I could prescribe to you a fixed course of action, regardless of what is observed in terms of uncertain events, like whether it's it's hot temperature for a week or a cold temperature. You're going to do the same thing. You're going to do the same fixed set of actions. I can prescribe to you, do this at this time, this at that time. And you don't need to reference. You don't need to take into account. You don't need to particularly know about, these factors outside of your control, like temperature. You're going to do the same thing. And the reason that's indicated is here, week 1, we are always doing nothing. Doesn't matter which way this branch went earlier, this uncertainty, this event, whether it was hot or cool, we're going to be making the same decision here.
Is the
that specified by like the darkened?
Yes. Oh, I'm sorry. I'm sorry, Jason. Yes, I forfeited my pedagogical duty here. Okay, I've got to modify these slides. Thank you. So the dark lines here are meant to indicate a decision rule. Okay, so that's meant to indicate, this recommendation. For every decision point, it's making a recommendation. Every decision point which you can reach. These ones you can't reach because it's saying go up this way if you get to here, so you don't need to fill it in. But these you're saying if you reach this point, you're going to make this decision. If you reach that point, and you're going to forego that decision. You're not going to make that decision. The dark ones are the ones you make. Does that make sense then?
The darkened line is like the available subtree.
Yeah, that's the one that we're saying for this strategy, for this rule, that's the one that's recommended. So if you get here, you'll make this choice. This could happen either way, so we don't have control. But if you get here, you'll make this choice. If you get here, you'll make that choice. Does that make sense?
So
yeah.
How is it? How is it static? Because in the decision on in between week 1 and 2, there's like current temp equals 20 and current temp equals 30.
Yeah, right here, like, or these. Okay, so remember, this is a great question, and I think it's so valuable you bring these to the fore. So, remember, which of these things do we have control over? Square ones. These are our choices. These things are events. Those are things we don't control. Our decision rule has to be able to handle whatever happens at this point. We want to be able to be there to provide guidance on what to do. So at this point, we can't control. Between the bug busters meetings every week at the health region and the city, etc., they can't control what the temperature will be in the next week. They need to have a plan in place that says, if the temperature in this week is high, do what? If it's low, do what? And so that's why it splits in that way, because we have to handle both of these cases. Here, we choose between them. We have the luxury of choosing which of these outcomes, and it's giving a recommendation. Well, here it's in this decision rule, it's saying do this at this one. But here we have to handle both. So the events, we have to handle all possible cases. The decisions, we're specifying one at each given decision point. So if you get here, you're going to make this decision. We don't specify it here because you can't get here. This is under your control. You choose this, so we don't have to specify that. Does that make sense, Jason?
That makes more sense.
Yeah. So here's static. Here's adaptive. Because here, we can't dictate which way this is going to go. But here, if we get a situation where we've seen a high temperature, we'll make a different choice than if after this point, we saw a lower temperature, then we'd make a different choice. We choose here, do nothing. This one, we choose larvicide. Does that make sense? This is a different decision rule. If I had to describe this one to someone, I would say, Corey, week 0, I don't have it labeled there, but week 0, do nothing. Week 1, do nothing as well. Week 2, you're going to larvicide. Week 3, and you note my description is, it says nothing about what the temperature is. It just says, do this in week 1, do this week 2, do this week 3. That's a fixed, predetermined plan. You see that? So you're always, you're always making the same, at each point in time, shown by these vertical slices, you're making the same choice, right? Whereas this one, you're making a different choice. For this one, if I had to tell Corey the decision rule, I'd say, week 0, you're going to do nothing. Week 1, if there's a high temperature, if I had to describe this rule to him, it would involve larvicide. If it were a low temperature, it would involve doing nothing. And so I have to make it contingent. And that's what makes it adaptive. It's contingent on the observation. It's contingent on what's been observed, you're going to make a different choice. Does that make sense?
Yeah. It seems like, I don't,
Mm-hmm.
like, looking at the graph,
Mm.
it looks like the decisions are made at the circles, not at the squares, because at the circle, like above the circle it has 20 degrees Celsius, and then below the circle 30 degrees Celsius. So I don't understand what is controlling the decisions made at the squares.
Okay, the squares. So very good question. I think this is terrific. You're bringing this. So you recall that with these types of nodes, with decision nodes, almost by definition, they represent situations where we have a choice, where we can select a certain outcome. It's there that we're trying to give a recommendation because it's there that we could choose which decision to make, what we want to do. Event nodes we can't control. It's like, will the temperature be high or will it be low? Well, I don't know. I'm not there to control it. So, here, it's true that there's a temperature here. We have to be able to handle either of those things. We're trying to create here a robust strategy that if it's high temperature, if it's low strategy, we can still give you a recommendation for what to do. And here, the event has different outcomes on each of these branches. We need to have a policy that we can give a recommendation any way it goes, because we don't have Saskatchewan weather is famous for being variable. We can't specify which way it's going to go, as inconvenient as it is. Whereas at the point of choices, that's something they do at the bloodless review. They say, okay, we're going to wait for now. We're going to issue an advisory for now. We're going to do source reduction now. That's what they can choose between. Does that make any sense?
Well, I think I understood it while you were talking, perhaps not to do with what you're saying.
Okay.
Yeah, so like, let's say it was 20 degrees Celsius. All of the circle nodes would be like, okay, you go up to the 20 degrees Celsius, and then in the circles at past week 3, those would also be determined based on the temperature.
Temperature then. So remember, this is with time, and so the temperature in this week will determine this one. The temperature in this next week will determine this one. The temperature in this third week will determine those. Those are all, and that may be a little bit confusing about this. When it says current temp, I mean the temp at that time. I don't mean that it's all the same temp. It's so if the temperature here, goes up, it'll go this way. If the temperature in week 2, maybe the temperature in week 1 is high, maybe the temperature in week 2 is low, in which case, what will actually play it over time is sort of a situation where we make this choice, this thing happens, it's high temperature, we do nothing, and then it's a low temperature. Only one of these scenarios will actually play it over time. Only one of the paths from the root to the terminal node will actually happen. But we need, in terms of giving recommendations, the whole idea is because for different scenarios, different paths, different things may be, different interventions, different choices may be more desirable. We're trying to give recommendations, essentially, that will handle any possible eventuality. They'll handle, if it's a warm summer, it's a cool summer, we'll give you sort of a rule to stick by that will give you at least a decent outcome for those situations. Does that make sense? And our choices early on are informed by the fact that we're going to have later these choices to make. And there's lots of things we're not going to know early on that we're going to know later. But by the later time, it may be too late. So it's all balanced. It's going to be balanced in there. Okay? So great question. Any other questions on this? Because this is important. So we have a static rule and we have an adaptive rule. People okay with that? Okay. Okay. So the primary, or a primary, I think it's probably fair to say it's the primary way people, the quantitative way people use these tools is to is to try to identify strategies that are most desirable. But it turns out that are most robust, the most effective decision rule, to give that sort of guidance. If this happens, do this. If that happens, do that. But there's some other analysis that can be done. That's quite powerful. For example, not only can you do strategy selection, but you can understand, for example, in terms of uncertainties in the model, which things will lead you to end up preferring one decision rule versus another, or one choice at a certain place versus another. You can look at value of information type analyses. So you can look at analyses which would say, well, if you could reduce the uncertainty about, say, weather. Suppose by this is implausible for weather, and I apologize. But imagine if by a serious investment, you could, maybe a better example, and forgive me for not doing weather, for switching a little bit the example, but one of the things that people in Saskatoon have to measure is what fraction of the mosquitoes are infected with West Nile. What's the fraction? And you can imagine one laboratory test giving you a rough and ready number, but with a lot of uncertainty around it. Another one giving a very precise number. Maybe you have to pay more for the more precise test. Then the question is, how much would that be worth? I mean, is it worth it to pay for this better test? After all, it's going to cost more up front, but maybe it'll actually improve our decision making so much it actually saves money on average. Maybe it's worth it. Another example that we're looking at in the West Nile context is, maybe it's worth it to pay for faster information. Maybe it's worth it to pay for a faster test that you get back in one day rather than a week, because that would greatly inform your choices in here. It would cost more up front, but it would make it would allow you to make bigger choices and therefore waste less money. So in these packages, and it's great to work with these things. So triage is a very popular one. At risk is another one. Crystal ball is another. Some of them work with Excel. Some are separate packages. But you can associate. Well, what's the difference, ladies and gentlemen, to get this engaged? What's the difference between this tree and the previous tree? Does anyone notice the difference? There's a subtle difference. This is a previous tree we looked at, almost. But what's the difference?
You don't have numbers.
You don't have numbers. Yeah, you have variables for the probability. And I told you the probabilities are often given in kind of a rough and ready sort of way. And so here, the idea is you could perform a sensitivity analysis and say, if I were to vary those probabilities, I'm putting in rough and ready probabilities, how far off would they have to be for me to change what decision I make there? How far off would they have to be for me to choose something different? And sometimes you get very interesting little spaces here where, you could have a broad set of uncertainties about probability of the OS being late and about, the likelihood that there's kind of a surprise in terms of unexpected incompatibility between your software and the other one. But in certain regions of the space, it may be actually very sensitive. So here we could have broad uncertainties for much of it, but if we're in these higher regions for possibility of the space and higher regions for probability of the slate, that's where we may need to not rely on those features. So you can do these sensitivity analysis, which show you in this sort of chart for what assumptions about these probabilities would you make one choice at this point versus another choice? For what assumptions about probabilities would you make one choice here versus another? And it can kind of map out, and that may give you solace. That may make you feel, I may be uncertain about this probability, but there's just like no way it's over 15%. And so I'm confident, in my reliance on these features. Or you may say, well, we really could be at risk, and the further out it is, the more we may be at risk. That, maybe we shouldn't rely on these features. So this software is actually really nice for doing this sort of stuff. Okay, and sometimes I should say it's more than about one number. As Dustin said, sometimes you want to take into account this, catastrophic risk, and you actually want to do it with a preference-adjusted outcomes. So you want to actually take into account utility values. In other cases, we care about multiple outcomes. We care about cost, time, quality, relationship with owner for software. Maybe we care about cost and deaths averted and damage to the ecosystem and a bunch of different outcomes. And there's a whole subfield of multi-attributed decision analysis, which takes these things into account. So it takes into account multiple attributes at the same time and tries to, this whole notion of the efficient frontiers, of optimality, and sort of what decisions at least do no harm with respect to other attributes, but still you don't want to leave things on the table. Like, given a given level of risk to human health, you want to optimize what's best for the environment, for example. And so they find ways of sort of accommodating these different needs under the same tree. And there's other ways you could try to combine them. Now, what does all this have to do with decision trees? And we're going to have to, finish up pretty soon and then finish up the lecture probably next time, this exact topic. But where does all this have to do? What is all this stuff with decision trees, which is an important part of this course, which I want you to absorb. What does that have to do with simulation? The whole focus of this course. Well, it turns out the two can be married very nicely. They can be combined. And we saw the basic rubric for this about half an hour ago, the simulation model and decision trees. We're going to have to play nicely together. And we're going to see how they can play nicely together. Okay? So the basic deal here is this. We have a framework which is designed to inform this kind of process of incremental decision-making, this process of adaptive decision-making, changing your strategy based on your observation, balancing learning with planning ahead. Okay? Captures uncertainty as time progresses, like decision trees, and it involves simulating a wide range of possibilities for all sorts of different outcomes. And trying to identify a decision rule, a strategy, what to do when, that is robust given that wide variety of outcomes. So you'll be choosing up front for that very first decision, bearing in mind, all the different eventualities which may play out. You might want to hedge your bet early on and say, okay, we know there's this broad range of uncertainties, so we're going to be deciding now to do some source reduction. Get that in place early on so that later you don't need to do larviciding. You can head that whole option off. You don't need to even think about adulticiding or anything. You head it off. So it takes into account kind of that broad range of uncertainties. And it allows you to recognize that there's this incremental decision making. We'll come back to this in a week, and we'll have more information then. We can choose that. So just sort of wait and see. And the idea is that we'll use it for diverse things. So what's the basic division of responsibilities here? Well, we saw it a little bit earlier on that slide with the sort of block diagram. But basically here, the simulation model is going to be responsible for calculating the dynamic consequences of scenarios, of sequence over times of events and choices. So, ladies and gentlemen, if we view this decision tree, the simulation model is going to be responsible for these terminal nodes. It's going to be responsible for saying, okay, you note this terminal node here, to make it simpler with the dart. We're going to simulate for this terminal node, the consequence associated with that is going to be coming out of the simulation model. It's going to produce that consequence by running the model. And it's going to simulate, okay, this decision happened, do nothing. And then there was a high temperature. And then we larvicided. And then there was a low temperature. And then we adulticided, and then it was a high temperature again. And it would simulate out the effects. It would simulate out the effects in terms of something we care about. Maybe it's deaths, or deaths averted, or say deaths. And that's the job of the simulation model. It's to sort of simulate these scenarios out. Okay? And then the job of the decision tree here. So simulation model is deterministic. As far as it should assume this upon week 0. Assume this choice. Assume this event happens. Assume this choice at week 1. It's all deterministic for a deterministic model. Some models are stochastic, in which case there'd be stochastics in the model. But in terms of the exogenous conditions, it would be deterministic, specified. Now, the decision tree, by contrast, represents over time uncertainties, represents decisions, and represents consequences. The normal things represent a decision tree. In decision nodes, in event nodes, and in terminal nodes. Not respective. I flipped the order of the first here. So the decision tree here takes care of encapsulating all the uncertainties, the kind of the policy space, the set of possible choices you can make, a set of possible eventualities. And a simulation model's job in life is to simulate particular scenarios. Does that make sense? Now, what's not obvious, but it turns out is quite key, is that there's a lot of common substructure here. We don't have to simulate every possible decision rule. It turns out there's an explosively large number of decision rules that could be evaluated. There's all these different rules. If this happens, do that. It's just a huge number. It's just intractably large for most problems. But there is, ladies and gentlemen, a huge amount of commonality between those decision rules. We can actually simulate terminal nodes. Moreover, if we cleverly simulate them, we can take advantage of common substructure in those decision nodes even. So, you'll notice that many scenarios share the same basic path here. Many scenarios, for example, this whole bunch of scenarios down here, share everything up to this point. Up to this point. So if we really want to squeeze the last bit, we could only do this part of the simulation once and then simulate after that many times. But there's even a huge amount between decision rules. I'm not going to be emphasizing that. So, for our case, for our application example here, simulation models are responsible, say, for the mosquito life cycle, bird life cycle, transmission between the two, human infection, totaling up costs and resource use. The decision tree represents the choices. Your choices over time, the uncertainties about temperature, for example, notably in that tree, and then various consequences. In terms of various outcomes we might care about. So we might have a system dynamics model, for example, for the underlying simulation. We have a decision tree, and then we end up basically simulating, in this case automatically. A student of mine, 1E, created a system for representing, visually interacting with, building up, and running these decision trees. And it will go run, Benson 50,000 times for these different terminal nodes, do a rollback to the tree and give recommendations at each decision point about which outcome seems most desirable given model assumptions at that point. So there's a framework that's been built up for actually running these things with these tools, where you can build up these trees, specify them, and have it executed. And what's going on here, I should emphasize, is nothing more than application of classic decision tree frameworks, in the sense the simulation model is evaluating these decision nodes, and then we're just doing a rollback, just in the classic case. Terminal nodes get the value from the simulation model. Decision nodes, you choose the best of their children. And event nodes, you choose the expected value. That's all it is. And then you then you can get recommendations at each point. The package allows you to systematically simulate all these terminal nodes, and therefore prevents you from having to manually do a lot of work, and it can handle very large trees. Okay, so those are some comments there. I want to make one final point. So we've been talking about vulnerability to uncertainty. We've been talking about this vulnerability to these exogenous conditions. And the problem, there's another problem besides just not knowing, what temperature is going to do and needing to plan. And what we've been dealing with is an extremely important class of problems. But there's something else that may be troubling you. It troubles me. It troubles me. Because, ladies and gentlemen, we live in an imperfect world. Our models are thinking tools. They're tools for capturing dynamic hypotheses. But just like those dynamic hypotheses in our head, the models we built are inevitably incomplete. They're inaccurate. They contain systematic biases, etc. And when we use them to plan, it behooves us to have humility, to have a certain humbleness in our recommendations, to recognize that we have limitations with our models. And one of the key things here, folks, is that we could have an extremely good model. It could be the richest agent-based model that someone could build, even given a lot of data. And we could ask it to simulate a situation. And probably at first it would be pretty good in terms of capturing many things about it, but it's inevitably going to diverge. It's inevitably going to diverge from the world because there's things that it omits that we can't possibly predict. Some of them like temperature, right? Some of them like rainfall. Some of them like economic conditions. All sorts of factors that we're never going to be able to realistically put into our model. And it's even the very best of models becomes outdated over time in that sense. That it's going to be making, say, a projection that's going to be off. Now, it could still be very useful, even at that point, for comparing relative outcomes of choices, but we're going to want to somehow update it so that it's responsive to current conditions. So it's not merely talking about the outcomes of choices as of 10 years ago or what have you. So, when you have a model, it's good to keep it updated. And we've been working in our work here with models that take into account uncertainty, so-called predictor-corrector models. And the idea is that you have a model which builds in uncertainty, and that uncertainty has an envelope of uncertainty that grows over time. There's some uncertainty of exactly how it evolves. And new data comes in periodically. And when the new data comes in, it regrounds the model. It ties the model down. And in this case, we have a model that's grossly in error. And so it's predicting things that are much quicker rise in the number of cases infected. And then a new piece of data will come in, and it will pull the envelope down. It'll say, oh, okay, I guess it was, it wasn't as bad as I thought. Boom. And then it starts growing, and okay, there's something going on here with the display, but okay, now I'm kind of on the ball. Okay, I'm on the ball. Oh, I'm overshooting here, so I'm going to bring it down. And there's a formal probabilistic way of describing this. It's based on computational statistical technique known as particle filter. And it systematically regrounds this. And ladies and gentlemen, the beautiful thing here is that even a highly fallible model, a very rough and ready model, where a lot of the parameters aren't known, there's a lot of uncertainty about the structure. If you ground it with data, even very noisy data, even data there's a lot of uncertainty about the data, you can have something where the whole is greater than the sum of the parts. You can actually have them feed off the best features of each of them. And the model may still, in the short term, be fairly accurate for prediction. Hugely more accurate than if you had just let it run open loop without regrounding it. And you're taking into account the fact that the data is noisy, and so not trusting the data as if it's come down from heaven, and the model is error prone, so you're not trusting everything to the model, and you're kind of taking each new piece of data, incorporating it in to our understanding of what's probably going on. and then you can project forward for some period of time. New data comes in, and you're always being kept honest by the new data coming in periodically to correct you. And the beautiful thing about it is, with even rough and ready models, you can do this sort of work to get a lot of value out of the model, even if it's known to have systematic errors, known to have big biases, known to have lots of aggregation, known to be off in some ways. It can prove actually quite accurate for capturing what may lie ahead until that next data point comes in. I don't have time to talk more about it. I'm going to be having a class next year on advanced modeling where we're going to be going into these sort of strategies more. But you should just be aware that there are techniques like this, and there's new innovations coming out which allow us to take models together with data and combine them to get the best of both and to guard against the weaknesses of each. Okay? So that's all for today. I've kept you a bit late, and I apologize for that. I wish you the very best with the problem sets. I am here to meet with people. If people need to meet about the problem set, I'm glad to do that. I remind people class is good, but I'm also glad to meet one-on-one. Okay? Thanks very much.